We can also show that the next wave function, or the next polynomial, x times this Gaussian, would be a solution. And you can show that the next energy level is 3/2 h bar omega naught. Well, when I take this second derivative, I'm going to have a few terms here. I'm going to have, after canceling out Gaussians, an expression that looks like 3a squared minus x squared plus x squared equals 2e over k. These two, of course, cancel out. And I'll get that e1 is 3/2 h bar k over m. Or e1 is 3/2 h bar omega naught. It's a good exercise for you to show what psi 2 looks like. It has the usual second order polynomial. And the energy levels of all these states looks like this. It's always an odd multiple of a half h bar omega naught. So for that reason, it's written as n plus a half. And again, notice what's built into this formula. There's a 0-point energy when n is 0, or the particle's in a ground state. The particle has an energy associated with it. Again, that's connected with the uncertainty principle. And what's interesting about this is that this was already shown even before the advent of quantum mechanics could prove it. In an article in Nature magazine in 1924, Robert Mulliken was able to show that various diatomic molecules, which are bound together by the covalent bonds, these kind of molecules vibrate back and forth, and as a result, when they absorb energy from a photon, they get kicked into a higher excited state of this vibrational bond. When they emit photons, they de-excite. And by looking at that the spectra, he was able to determine that the spectra better made sense if one had already a 0-point energy in the system. In general, these wave functions follow the pattern I've just described. The quantum number goes up by 1 unit, but the energy eigenvalue is always an odd multiple. And there is a regular description for these polynomials. They're called the Hermite polynomials. That's probably not particularly important for us to remember. But do remember that they go like the 0th, 1st, 2nd, and so on, power of x. Perhaps something more important to remember is that they alternate whether they are even or odd. So notice that the 0th polynomial is an even function of x. The first polynomial is an odd function of x. The second polynomial is an even function of x again. So notice there's no x term in here. It's just x to the 0 plus x squared, and that's because this wave function is an even wave function. The third n equals 3 wave function has only the odd polynomials in it. so x and x cubed, and the fourth has only x is 0, x squared, and x to the fourth.